Topic of my talk today is perspectives in math and art. So, mathematics, as you know, is an essential tool for understanding science, right? You must have, in your science class, to analyze anything, you need mathematics, especially sciences like physics and chemistry. Now, actually, biology has also become quite quantitative. So you do need mathematics as an essential tool for understanding science. But what is somewhat more surprising is that mathematics also has connection to art. So, yeah. So that's what we are going to talk about today. Art, science, math, it's all a continuum. There is no real divide. The divide is sort of artificial. And the topic of my talk today is the bridge between mathematics and art, right? So as I said, the topic of my talk is perspectives in math and art. So let's start with these two paintings. So the painting on the left is a painting from thousands of years back. It's cave art. And the painting on the right is from the 1600s, during the European Renaissance time, made during the European Renaissance. So what is the central difference that you noticed between these two paintings? So can somebody answer? Yeah, what is it? Time period, of course, that's an obvious difference. But looking at the two paintings, what do you see is different? Oh, yeah, right. Hello? Complexity, that's a good point. The one on the right looks much more complex than the other. Any other response? Yeah. Geometric difference. Good. So what do you mean by the geometric difference? Shapes are clear cut. Okay. So there are shapes in both paintings. No? So what do you mean by a clear cut difference in shape? I mean, it's getting there. Something else? Anybody else has anything else to contribute to that? The painting on the right looks more three-dimensional, doesn't it? Than the, yeah? So I think that is the central difference. You were all hinting at something like that. Probably you wanted to say something like that, but I think that is the real main difference. So both paintings are appealing in different ways. So in art especially, it's hard to say which is better and which is worse. Some things appeal to some people, other things appeal to other people. So we can't really say that this is better than that. But there is an obvious contrast between the two paintings as we discussed. So the painting on the right gives a feeling of depth which is absent in the painting on the left. So we will dwell into the mathematics behind the feeling of depth that paintings like the one on the right create. Okay? So Renaissance art, this Renaissance period provided a space for a rich interplay between art and mathematics. And the mathematics that was born out of this interaction is called projective geometry. So notice that the parallel lines on the floor, when extended, meet at a point, and that point is called the vanishing point in the painting on the right. Let's go back to the painting on the right. Right? Now look at this. Look at the floor tiles in the painting on the right. Yeah? You just keep following those floor tiles further down. You see that they appear to meet at a point on the canvas, right? So that point is called the vanishing point. Now, so what did I tell you just now? I told you that parallel lines, which are lines, the floor tiles that you see on the floor, which is depicted in that painting, they actually meet at a point. Isn't it different from what you have learned in school? right? In Euclidean geometry in high school, you have learned that parallel lines do not meet, right? So this is clearly quite a different concept that you have come across when you come to the art, Renaissance art, or more precisely the mathematics that was born out of Renaissance art. This is projective geometry. So in projective geometry, what we are finding is parallel lines actually meet at a definite point on the plane of the canvas, or the plane, or the, in mathematical terms, on the projective plane. Right? This is already a new idea that you have come across now. In fact, this is not as unfamiliar as it might strike you. In the mathematics class, you have learned this abstract idea that parallel lines do not meet, but what is it? What is it? Each other, okay, whatever. Okay, do not parallel, if you want to add each other, fine, but yeah, so the idea is that the parallel lines do not meet. So, but all of you, I'm sure all of you are familiar with a view like this, right? You have all traveled by train and you have seen railway tracks. And what are railway tracks? Railway tracks are parallel lines. But if you follow the railway tracks, you find that they appear to meet at a point on the horizon. So these are parallel lines that meet at a point, finite point. This is the idea that is captured in projective geometry. So Renaissance artists appreciated this idea, they noticed this, and apart from the geometric concept of these parallel lines meeting at a definite point, they also added some extra meaning to that special point, the vanishing point. For instance, this is a famous painting from the Renaissance time. It's made by the great painter Raphael. And notice that at the vanishing point, there is a significant figure placed. That figure of an orange-robed person, that is Plato. And next to him is Aristotle. And if you really look at the painting in detail, you see that it captures the very special atmosphere of the Renaissance beautifully. It covers every endeavor of the human mind, whether it is art, mathematics, science, philosophy, everything is depicted in some form in this painting. And in one corner, on the rightmost corner, you'll see a small painting of a head over here. That is actually the painter himself. Raphael's face is depicted in one corner. So the vanishing point, the point at which parallel lines meet, is given a special thematic significance also by the Renaissance painters. So projective geometry, let's go over a brief history of projective geometry. So in 300 AD, Papals' theorem was the earliest theorem in projective geometry. In 1600 AD, which is during the Renaissance time, Pascal's theorem was formulated. It's a generalization of Papals' theorem from straight lines to conics. So Papals' theorem had to do with straight lines. So Pascal's theorem is essentially Papals' theorem translated to conics. Conics, you know, are sections that you get, yeah, conic sections. So basically you take a cone and take a plane, and depending on how you cut, how you slice the cone, you get different curves, parabola, hyperbola. So yeah, exactly, all these things. So in the 1600s, there's a significant theorem that was formulated, which is a significant theorem in the realm of Renaissance art also. It's called Descartes' theorem. Descartes was an engineer, mathematician, who was interested in art. So he was all of these. This is an example of the fact that there is no barrier between all these endeavors. So around the time of Descartes' work in the domain of projective geometry, Descartes and others introduced Cartesian geometry. So I'm sure all of you have come across Cartesian geometry, like coordinate geometry, what you call. So you have x and y coordinates, axis, and then you can draw various curves. So that is coordinate geometry and Cartesian geometry. So what happened is that there was a dominance of Cartesian geometry and calculus, and there was a consequent and subsequent decline in the interest in projective geometry. There was, however, a re-emergence of projective geometry in the 1800s thanks to the works of Mobius, Klein, Chasselet, and others. These are all advanced topics. I won't dwell into it. But Mobius, the name Mobius may be familiar to many of you. Have you come across the Mobius strip? Have you heard of the Mobius strip? No, okay. It's maybe a somewhat advanced, but it's an interesting idea. Suppose you take a strip of paper. Suppose you take this strip of paper, right? And if you identify the two ends, what you get is a cylinder, right? On the other hand, if you introduce a half twist and then identify, what you get is called a Mobius strip. I don't know whether I can, let me just see if I can tear it and show you. So this is a cylinder, right? This is just a cylinder. But if you introduce a half twist and then add, this thing is called a Mobius strip. And you can have a lot of fun painting a Mobius strip. I'll just give it to you as an assignment. Just try coloring the Mobius strip and see what happens. And see what is different between a cylinder and a Mobius strip. Okay, I won't give away the answer, just try it. So the basic notions in projective geometry are meets and joins. So what is a meet? The intersection of two lines is a meet. So if you take two lines, and here say the one line is capital L, the other line is capital M, then the meet is called capital LM. And consider 2 points, little a and little b, and imagine joining the 2 points. That is called a join, that is little ab. These are the basic elements of projective geometry. Now, Papals' theorem, as I had mentioned earlier, can be stated in this way. So consider this blue, there are 2 blue lines, you can see, and the one blue line has 3 points, A, B, and C. And the other blue line has 3 other points, A prime, B prime, C prime. Now consider joining these points crosswise. Say you connect A, B prime and B, A prime. The intersection is a red point, as you can see in the figure. Then you join B, C prime and C, B prime. That's an intersection, which is another red point. And connect A, C prime and C, A prime. That is a third red point. So Papals' theorem claims that these 3 red points lie on a single straight line. That's the statement of Papals' theorem. I just want you to appreciate the statement of this theorem. Have you noticed a big difference between what you come across in Euclidean geometry and what you see in this projective geometry? In Euclidean geometry, you typically prove theorems involving the congruence of triangles, for example. Then angular measures have to be stated. And length measures also have to be stated. What is the size of a line segment? Notice the complete absence of any mention of length measures or angular measure. That is the nature of theorems in projective geometry. So in projective geometry, all lines are extended. They are not line segments. And there is no reference to any measure. So Pascal's theorem, as I had said earlier, is basically a generalization of Papals' theorem to conics. So here, instead of those 2 straight lines which we had now, we have an ellipse. An ellipse is an example of a conic. So this diagram shows an ellipse, and you have the 6 points on the ellipse, A, E, C, F, B, D, right? And now you consider joining them crosswise, as we had done with Papals' theorem, right? So when you join these lines crosswise, you find these 3 white points. And the claim in Pascal's theorem is that these 3 white points lie on a straight line, single straight line. Again, notice the absence of angular measures and measures of lengths of line segments in the statement of this theorem. Now, projective geometry is actually even simpler than all this in a sense. You don't even need to think in terms of curved lines and so on and so forth. It is actually the geometry of the straight edge or the ruler that you are all familiar with, right? So for instance, conics can also be generated by the use of only a straight edge. That sounds paradoxical, but it's true. If you look at this diagram over here, it's a family of straight lines which is describing an ellipse. So there is a way of doing it. I won't dwell into it. There's a YouTube channel where you can just type in how to generate a conic using straight line. And it's very interesting. You can go over it. But it's simple at some level. You can all understand it and master it. So conics, as I said, this is just a diagrammatic representation of conics. You have a double cone and you take this plane and slice it. Depending on how you slice it, you generate different conic sections. Hyperbola, parabola, circle, ellipse, and so forth. Now, projective geometry, as I said, is math born out of art. So the Renaissance artists realized that parallel lines meet at the horizon, as we have discussed already. Straight lines must be represented by straight lines. Okay? And the image of a conic is also another conic. So, for example, the image of a circle, when mapped onto projective plane, can become an ellipse, for instance. But it will remain within the conics. So, projective geometry thus sets an equivalence between all conics. So, in a way, it's reminding us of the common origin of all the conics. So, as I had said in the last slide, that whether it is hyperbola, parabola, circle, or ellipse, all of them are generated by taking a plane and slicing the cone. And so, although they may look in detail, they may appear to be different, they have a common origin. That's what projective geometry is reminding us. So, to be more precise, let's consider a definite example. So, in this board drawing over there, you can see on the right-hand side, there's a parabola drawn. So, that parabola, you think of it as being drawn on the Cartesian plane. As you know, you have all done coordinate geometry. So, in the Cartesian plane, you have a set of parallel lines parallel to the y-axis, set of lines parallel to the x-axis. And if you have a parabola, which is described by the equation y equals x squared, you can find out the points and make the parabola. Now, the question is, what happens to the parabola when you map it to the projective plane? So, this is where something interesting happens. As we just remember the railway track effect. No? So, if you have a set of parallel lines, they actually converge at a point. So, lines parallel to the y-axis in the projective plane will converge at a point. Okay, so that's what you're seeing on the left-hand side picture. That's the projective plane. So now, if you take this line, so what are the points on the parabola? 1, 1. So what happens in the projective plane to that point? That will be mapped to 1 point. Then the next point is 2, 4. That will go up there, and so on and so forth. And then you keep track of all the points. What you end up with is an ellipse. So it's interesting, right? A parabola in an ordinary Cartesian plane gets mapped to an ellipse on the projective plane. So that's likewise, you can see many different examples of different conics getting mapped to something else when you map it to the projective plane. That's an interesting feature of projective plane, that it sets an equivalence between all conics. So both Descartes and the artists realized that points at infinity need to be added to represent the horizon. This is needed both for art and mathematics theorems. For instance, Descartes' theorem or Papals' theorem. One hallmark of projective geometry, as I had mentioned over and over again, absence of reference to any measurement. Unlike Euclidean geometry, for instance, all lines are extended in projective geometry. So projective plane is basically the ordinary plane plus the line at infinity. So I had talked about this point at infinity, a set of parallel lines joining at a point. But you can have different sets of parallel lines meeting at different points, right? Now you imagine joining all these points, then you'll get a line. That's a line at infinity. So in a projective plane, any two lines meet at a point. Yeah, this is different from Euclidean geometry. Euclidean geometry will say non-parallel lines meet at a point, but parallel lines don't meet. But here in projective plane, all lines meet at a point. Given any two lines, they meet at a point. Okay? In a projective plane, any 2 points join to make a line. So look at the symmetry between these two statements. As if in the first statement, if you just interchange points and line, you get the second statement. Right? Isn't it an interesting feature of this geometry? So thus, there is a duality between points and lines in projective geometry. So Poncelet was a person who was born during the French Revolution, and he indeed brought about a revolution in the realm of mathematics. Right? Poncelet was a very significant figure in the realm of projective geometry. So projective geometry, there are two key principles. One is the principle of continuity. So if you look at this diagram over here, you have a set of lines. They are meeting at a point. But imagine tilting these lines along the arrows that are shown, right? Then what do you end up with? You end up with a set of parallel lines, isn't it? Can you see that happening? So there is a continuity between non-parallel lines and parallel lines. There is no real distinction between non-parallel lines and parallel lines. That's something that projective geometers recognized, in particular Poncelet, who thought about it afresh, recognized. And the other one is the principle of duality, which I was talking about earlier, that there is you can comfortably interchange the roles of points and lines, and things continue to make sense, as if the roles of points and lines are interchangeable. So if a theorem holds in the projective plane, its dual holds in the dual projective plane. Thus, there are duals of all the theorems that we were talking about. Papals' theorem, Pascal's theorem, Descartes' theorem. All these have counterparts in the dual projective plane, where all you have to do, you take a statement of any of these theorems, interchange the roles of lines and points. Then you find that that statement is also a valid theorem. That's the interesting feature of projective geometry. So here I've mainly talked about mathematics, but I thought that I'll just dwell on art a little bit. So projective geometry through drawing. So this is an illustration of Dürer's perspective machine. Dürer was a very famous Renaissance artist, and he had a perspective machine which looked like this. So it consisted of an object. There's a lute or something over there. The picture plane, on which the picture has to be drawn, and the eye of the artist over there. So for instance, many of you said that you were interested in art. You can think of, consider drawing an apple on a table. It's a very simple exercise. So so the canvas is placed between the object and the eye, right? And the drawing is constructed by connecting the intersection points of the sight lines and the canvas. What are sight lines? The sight lines are the lines joining the eye to the object. So I'll clarify it better. This clarifies what I'm trying to say. So drawing of a flower in a box. Here you have the eye, here is a 3D object of the box and the flower, and this is the canvas, picture plane, and you see these sight lines piercing the picture plane at various points. And you join them and you construct the painting. And all these Renaissance artists came up with interesting devices to represent the three-dimensional world accurately. So, for instance, there was this Brunelleschi, who was a 15th century Italian architect. He had a way of doing this by using a mirror with a hole. I won't dwell on it. There is a YouTube channel where you can look up about Brunelleschi's mirror with a hole. It's interesting. Then the great Leonardo da Vinci had a device called a perspectograph. And till now I have talked about actually one-point perspective. That means that a set of parallel lines merging at a point. That was the first painting that I had shown you. But in general, you can have families of parallel lines merging at various different points. So here there's a two-point perspective. So apparently, this is just a historically interesting piece of knowledge. The notion of a two-point perspective was first seen in 1505. And as I said, that there can be various different families of parallel lines meeting at different points, and then you can join them and construct a line. So here, these are floor tiles. You have a set of parallel lines meeting at one point, set of diagonals meeting at yet another point, a set of parallel lines again meeting at yet another third point. Now, this is a very interesting object. It's called the Camera Obscura. I think you must have studied in your physics class. You must have come across the pinhole camera. Yes. So this is a pinhole camera. So pinhole camera is a physics device which artists came up with. So this is again an example of merging of art and science. So here you see an artist sitting inside a room which is essentially a pinhole camera. So you see a hole in one of the walls, and in the opposite wall, the landscape which is outside, the image of it is projected. And what is this artist doing? The artist has placed his canvas on that wall. And all he has to do is to take his paintbrush or pen or whatever to draw the outline of this image. But notice that the image is upside down. That's what happens in a pinhole camera. You get an upside down image, right? So it's upside down, but to get it right side up, all he needs to do is turn it around, right? And he gets a beautiful drawing of the landscape. So this is a device that Renaissance artists used to use. And it's a device that you encounter in your physics class. So that's why it's always good to be in touch with various domains of human endeavor, whether it's art and science. Nothing is higher up than others, and I mean, there's no hierarchy here. I mean, it's meaningless to say that science is higher than art or art is higher than art. Art is higher than science in a sort of a caste system of subjects. It always pays to have some understanding of every part of human knowledge. So, interestingly, elements of perspective were present in medieval European art also. So this is a piece of art from 1389. And notice that the artist does have a notion of perspective, in the sense that things which are far away look smaller than the things which are closer by. And what is even more interesting is that way back in 59 to 79 AD, CE, in Pompeii, is an ancient relics, Roman relics are there. And there they have noticed that artists have used the notion of perspective. In fact, I have seen it with my own eyes. I had visited Pompeii because there was a conference I had to attend in Italy, in Napoli, and from there I went to Pompeii. And I was struck by these frescoes, which were made in really ancient times, which showed the sense of perspective. So, although there were examples of perspective in art prior to the European Renaissance, the merging of mathematics and art happened only during the Renaissance. An intuitive understanding of perspective was always there amongst early artists. However, a comprehensive understanding emerging from the interplay of art and math did not happen before the Renaissance. So, this is, I'll just state Descartes' theorem. Descartes' theorem was a very central theorem formulated during the Renaissance time. So, it says that if two triangles are in perspective via a point, they are in perspective via a line. So, what is the statement? So, can you see the two triangles ABC and A prime, B prime, C prime? So, they are in perspective with respect to the point O. Okay? So, the statement is that if they are in perspective with respect to the point O, they are in perspective with respect to this line L that you can see. At the bottom, can you see a line L? Little l. So, actually, the statement of Descartes' theorem can be rephrased in the following manner. If you have two triangles which are in perspective with respect to a point O, consider extending the corresponding edges of the triangle, and then you get intersection points, right? You'll get 3 intersection points. So the claim is that these 3 intersection points lie on a single straight line. So how does one prove it? Notice, you must be familiar with the idea that the intersection of 2 planes is a line, right? So if I just tear this thing, if I take these 2 planes, you see that they intersect at a line, right? So you have 2 triangles, one ABC and the other one is A prime, B prime, C prime. They are lying on 2 different planes, right? And now, if you consider the edge AB, that line, so let's call these 2 planes P and P prime. P is the plane on which ABC lies, P prime is the plane on which A prime, B prime, C prime lies, right? So, now consider extending AB and A prime, B prime, right? They will intersect at a point. Now, not only that, they will also lie on the line or at which the 2 planes intersect. Do you see that? That is simply because AB lies on the plane P and A prime, B prime lies on the plane P prime. So the intersection point of those 2 lines will lie on the intersection line of the 2 planes on which they lie, right? This is clear, right? So the same thing will happen for BC and B prime, C prime. If you extend it, they meet at a point. That point lies on the line at which the 2 planes intersect. Same is true for AC and A prime, C prime. When you extend them, they'll meet at a point. At that point will lie on the line of intersection between the 2 planes. So that's it. We have proved the theorem, right? So it's so simple. It's deceptively simple. It's almost like you're making the statement of the theorem and it's a proof. This doesn't usually happen in Euclidean geometry. You have to work hard to prove theorems. So just to conclude, European Renaissance saw the merging of art and mathematics. Projective geometry was born out of that intersection. Projective geometry offers a path for artists to appreciate mathematics and for mathematicians to appreciate art. Projective geometry is indeed the most fundamental and the underpinning of all other forms of geometry. So I'll end with a statement by the great Leonardo da Vinci, who was as much of an artist as a scientist. Art is the queen of all sciences. Thank you. And here are a couple of references. You can look at.